Now that we've finished our section 3.1 notes, exponentials and logistic functions, we get to enter some of my favorite mathematics, logarithmic functions. Not so much the graphs, but logarithmic functions is one of my favorite things. Why? Because it's the first mathematics that I failed. I failed the log chapter when I was in high school. It was bad. I knew diddly squat. It was not my teacher's fault. I was withdrawn from school for a month, had to go somewhere for a month. And where I went to another school, they were not on block scheduling like I was. So while I was at the other school, they were several chapters behind where I would have been had I still been in my school. And when I went back to my school, I had missed the entire logarithmic chapter and had to teach it to myself. And you can imagine how well that went. So I failed that chapter. It's the first mathematics that I was unable to do in my life. I made them my job to master because I am not okay with not knowing mathematics. I love mathematics. It's my poetry. So now I'm really good at them. And not only am I good at them, I'm good at teaching them. That's right. Tooting my own horn here. I think that by the time I'm finished with you, they will no longer be magic. You will look at a logarithm and go, yeah, well, that's just math. I'm telling you, it's simple algebra. And if your Algebra 2 teacher did not teach it as simple algebra, that's because they thought it was magic also. So here we go. The logarithmic function starts with my very absolute favorite thing to say about mathematics. Anything that can be done can be undone in mathematics. There is no such thing as a one-way operation. This means that if there is a way to raise constants to a variable exponent, an exponential, there must be an algebraic operation, a way to isolate that variable. Enter the logarithm. The logarithm is nothing but an operation. So what makes it confusing is we don't have a symbol for it. But logarithm is a symbol. It's like plus, or square root, or divide by. It's an operation, and that's all it is. And every operation in mathematics has a job. Undo another operation. Plus and minus, inverse operations. Multiply, divide, inverse operations. Square and square root, inverse operations. Exponential base, logarithmic base, inverse operations. Their job is to cancel one another. You will see what the inverse is. I have a board problem though. Let me see if I can fix this. Fit the height, fit the width. There we go. We are fixed. Logarithms are the inverse operation of raising a constant to an exponent. You learned about that in 3.1. And inverse functions are nothing but a reflection over the line y equals x. So the blue curve there is y equals b to the x, an exponential growth function. The black curve is y equals log base b of x. It is not an accident that I use the letter b again, because if the bases match, they're inverse operations. And that's why you see that as a reflection of the line y equals x. This is the parent logarithmic function. So the very first thing that your Algebra 2 teachers probably did with logarithms was had you convert between exponential form and logarithmic form. And they probably showed you some little cutesy trick with an arrow, right? Maybe you don't even remember. I never, ever want to see you do this, but if I said, 2 to the 3 equals 8, this was exponential form. And if I said convert this to log form, a lot of Algebra 2 teachers are like, okay, you just do it like this. And so you get log base 2 of 8 equals 3. And so on and so forth. It was just a quick, cutesy little trick, converting between logarithmic form and exponential form. But here's my question to you. Did you ever fully understand what that meant? Or were you just getting answers? You're just getting answers, right? And you felt successful because you could get an answer. But you had no idea what you were doing. Ich wünschte, ich hätte ein A. That's German. Now, I could teach you to repeat what I just said, and you could probably repeat it perfectly. That doesn't mean you understood what you said. Ich wünschte, ich hätte ein A is German for I wish I had an A. And as long as you understand these things, you will get an A. And trust me, I can get you to understand them. So the basic rule is if x is greater than 0, and this is necessary, and your exponential / logarithmic base is bigger than 0, but not equal to 1. So we have the exact same rules as we did for exponential growth and decay. The base must be a positive number, but it cannot be equal to 1. Same exact rules. What we have here is that log base b of x equals y if and only if, which means this is a two-way street, b to the y equals x. And you're like, okay, well, that hasn't really cleared this up for me. I don't understand what this is saying. What this is saying is these operations can cancel one another in either order. For example, if I gave you 2 to the x equals 16, you could probably easily tell me what this answer is, right? What is it? 4. But let me ask you a question. What algebra did you do to get that answer? Ah, you just knew it. Could you imagine if I taught you that way? Well, I just know the answer is this. You don't? Could you imagine how difficult life would be, right? So there must have been an algebraic process that allowed you to isolate your answer. And there is. So what I would say is, well, what's the problem? How do I get x by itself? The problem is I have an exponential base 2. If only I had a way to cancel exponential base 2. Oh, wait a minute. That's right. Exponential base 2 is technically an operation. I must be able to undo it with its inverse operation, a logarithm. And they have to have matching bases. So what cancels exponential base 2? Log base 2. So what you would do is you would take the log base 2 of both sides. Because this is an operation. It does not have value. It's an operation. That would have to be done to both sides. Now the log base 2 and the exponential base 2, since they have matching bases, cancel each other out. Your exponent falls to the ground, and the solution is x equals log base 2 of 16. X has been isolated. At this point, you're allowed to say, I know that answer is 4, because x has been isolated. This is the algebraic process. What you probably weren't taught is that log base b says, what power of b? That's what it says. So log base 2 of 16 says, what power of 2 gave me this 16? And the answer is 4. That's what log says. Yeah. Mm-hmm. They're inverse operations. So when we're going to evaluate these logarithms, we are not going to say we just know the answer. Instead, we're going to use the idea that a logarithm has a job, and we need to let that logarithm do its job. And its job is to cancel a matching exponential base. So for the first one, log base 2, it has a job. Its job is cancel exponential base 2. And it can only do its job if the argument, which is what you're taking the log of, so in part A, the argument is 8, is if the argument has a matching base. Let me ask you a question. Is 8 a base 2 number? Can it be written as a power of 2? Woot. Cool. Then let's do that. Log base 2 of 2 to the third power. Well, log base 2 cancels exponential base 2. Your answer is 3. That's the value of log base 2 of 8. Log base 2 is an operation. Its job is cancel exponential base 2. So if I can write my argument as a power of 2, log base 2 will cancel that exponential base 2 and leave behind the exponent as an answer. It's not magic, it is algebra. It's an operation. Log base 3 has a job. Cancel exponential base 3. Can square root 3 be written as 3 to some power? Yes. Then yay. That means log base 3 will be able to do its job. This says log base 3 of 3 to the 1/2. Log base 3 will cancel the exponential base 3, leaving you with the answer, 1/2. It's not magic. It's an operation. That's why it doesn't have value, because it's an operation. What's the value of plus sign? What? You can't ask the value of an operation. That's why you can't, like, students are like, oh, you divide both sides by log. Like, what the F did you just say? Log is, oh, I'm going to divide both sides by plus sign. Like, you can't say things like that in mathematics. It's an operation. It does not have value. It has a job. Log base 5 has a job. Cancel exponential base 5. 1 over 25, lucky for us, is a power of 5. 5 to what power? Not -3.
Squared?
No, look here. Log base 5. 5 raised to some power gives me 1 over 25. It must be negative because it's a fraction, and 2 because 5 squared is 25. Log base 5 gets to do its job, whee, and leave behind -2. Ah, the next one. The last two, actually, these are special logarithms. They're special. The first one's special because the argument is 1. Okay, log base 4 has a job, right? Log base 4's job is to cancel exponential base 4. That means I need to be able to write the number 1 as something that's base 4. Ah, someone said it, to the 0. Oh, there it is. Oh, okay. Log base 4 is 0. Special log rule for you. Log base b of 1 equals 0. It does not matter what the base is as long as you haven't broken the rules of the base. Base must be positive, cannot be 1. It doesn't matter what that base is. Once the argument equals 1, the logarithm has a value of 0. This is the other special logarithm. Log base 7 has a job. Its job is cancel exponential base 7. So 7 can be written as 7 to the 1, which means log base 7 of 7 equals 1. So anytime the base matches the argument, the logarithm has a value of 1. As long as you have not broken the rules of the base. Must be a positive number, cannot be equal to 1. It cannot be a negative number because it must be a positive number.
Yeah, but what do you get if it does?
Logarithms of negative things only exist in the complex plane. There's some pretty cool videos on it on YouTube. If you're interested, Red Pen, Black Pen has some really, really good stuff. Or is it it's Black Pen, Red Pen. The letters come alphabetically. It's Black Pen, Red Pen. He's got some amazing videos. So here's the basic logarithm properties. Remember, x has to be 0, base has to be positive, cannot be equal to 1. So for any real number y, we get that log base b of 1 equals 0. How come? Because b to the 0 is 1. That's why. And log base b of b equals 1. Why? Well, because b to the first equals b. That's why. Log base b of b to the y equals y. How come? Because log base b has a job. Cancel exponential base b. That's why. That's why it says inverse operations cancel one another. And now this last one, whoo boy, doesn't that look special? B raised to the log base b of x automatically equals x. Because inverse operations cancel one another. So not only does log base b cancel exponential base b cancels log base b. In either order.
But you can't divide if there's visible, right?
You're not dividing. You're not dividing. It's all exponential style stuff, so no division is allowed. Now, before we go on to further examples.
Some other way.
Sure. Let's see. The last one, some other way. How about I use actual numbers? 2 raised to the log base 2 of 3. If log base 2 has a job, log base 2's job is to cancel exponential base 2, right? Well, inverse operations work in either direction. plus cancels minus, minus cancels plus. So if log base 2 cancels exponential base 2, it must also be true that exponential base 2 cancels log base 2. In either order. And that's all that last bullet is telling you. It's showing you that the exponential and the logarithm will cancel each other in both orders, as long as the bases match. And I feel like that is the perfect place to stop because we have been introduced to the idea of the logarithm.